Hi, my name is Amir Adeli, postdoctoral researcher at the University of Adelaide, and the title of project that I'm presenting is Geostatistical Approach to Validating Geological Loggings. The supervisors are Professor Peter Dowd and Associate Professor Chaoshui. My project is Project ATP12, second part of Translation Project 1, and it is located here between exploration and evaluation projects. The ultimate objective of this research project is to provide geostatistical algorithms for validating geological core logging when quantitative variables are available from geochemical analysis or geomethods. At first, I will talk about the motivation to do this project, then explain key findings and the proposed algorithm, then discuss the significance of this study to industry and talk about the future work. Motivation for doing this research. Visual nature of geological core logging makes the classification to be qualitative or semi-quantitative and subject to some errors. So it is necessary to validate geological core loggings before using as a basis for resource estimation. What if we don't work on this topic? By answering these three questions, it will be somehow clear the situation if we don't follow the topic. First, how do inaccurate logs affect? Inaccurate logs generate geological data inconsistent with chemical analysis and metallurgical tests. For example, low iron grades will be seen in supergene hematite zone, which is not logical because geological data from logs and chemical analysis and geomethods are explaining the same events, so they should be consistent. Second question, is it possible to perform relogging? No, according to the limited time and resources, it's impossible. And these inconsistent data are often treated as outliers or simply ignored in the geological modeling stage. And the last question, can inaccurate logs be detected based on information of quantitative covariates? For now, there is not a developed objective approach in this field. This research is based on these considerations. First, geological features such as lithology and quantitative covariates such as chemical analysis and geomethods should be consistent in spatial and statistical terms as they are related responses to the same geological processes. Also, most of the data are correctly logged, and we suppose that chemical analysis and geomethods are more accurate than geological loggings. Here, an algorithm is developed for validating geological loggings to identify data for which the logged category is not in agreement with quantitative variables. This will affect on all following steps in the mining process, including to improve the quality of mineral resource models. The main steps here include the following. First, geological domaining, and then transforming into normal scores, then covariance analysis. The next step is leave-one-out cross-validation, which for each sample it should be assumed having each of the available rock types once and doing the cross-validation, then repeating it for all the available rock types for the same sample, then repeating it for all the samples. At the end, calculating p-value for each sample and each rock type, which gives a measure of remoteness between the expected value and the true value for the specific sample and rock type. And by comparing these p-values, it can be found the most appropriate rock type for each sample. It's easier to explain the leave-one-out cross-validation step with an example. So at first, we select a drill core sample
and assume that it belongs to category 1, which is CLBX, and do co-creating all the continuous variables, these 10 continuous variables for the Diricole sample under consideration, using all surrounding Diricole samples. Then calculate vector of co-creating predictions and variance covariance matrix of error related to category 1. So we will have prediction of CU2, prediction of IU1, FE1, S2, IL3, CR2, LR1, CAR2, MG2, TI2, and variance covariance matrix of error related to category 1. Then from there, we should calculate the Mahalanobis distance corresponding to the vector of true values for category 1. Then repeat all these for category 1 to category 12, and then repeat. So we will have Mahalanobis distance for all possible categories for that sample. Then repeat for all these steps for all the samples.
In Calculate, p-values are used for finding suspicious data. For each Diricole samples should be done the following steps. Should be checked all the samples, Diricole samples with a distance less than 20 meters from the selected sample, and check their rock types. And if at least one of their p-values is greater than 0.5, it means there is a very good candidate, while the p-value of the currently rock type is very low, is less than 0.02, which means the currently rock type is very unlikely, but there is a candidate in less than 20 meters distance from this sample, which is very highly probable. So if a Diricole is meeting these conditions, it is representing an alarming point, and it should be checked and revised case by case. About the prominent heel case, about 0.6% of the Diricoles are identified as suspicious data based on this method and the numbers that suggest. The proposed algorithm is not a black box, as it allows the practitioner to include additional criteria and to be more or less conservative in identifying suspicious samples. And another thing is about, as we know, the information gathered from geological core logging is the basis for constructing geological and geometeorological models for mineral resource evaluation and classification, ore reserve definition, and mine planning. So also in the same way, it's very important revising them and reclassifying the suspicious loggings or removing them. So it's very important, it affects in all the following steps in the mining chain. And also here we have provided a practical approach for validating petrophysical attributes, not just the lithology. It can be used for alteration, also for mineralogical assemblage. The proposed approach can be applied in several geometeorological contexts, for example by using geochemical data as covariates for defining lithologies, or mineralogical data from ChemScan analysis for finding mineral zones, or gang mineralogical data derived from spectroscopy for recognizing alterations, or all the previous types of data, as well as metallurgical tests for identifying geomet domains. And at the end, thanks Professor Peter Dowd and Associate Professor Chaoshui for their supervision, also OzMineral and Consortium for their support.